In the past few decades, deep learning has proved to be a very powerful tool because of its ability to handle large amounts of data. The interest to use hidden layers has surpassed traditional techniques, especially in pattern recognition. One of the most popular deep neural networks is convolutional neural networks. Since the 1950s, the early days of AI, researchers have struggled to make a system that can understand visual data. In the following years, this field came to be known as computer vision. In 2012, computer vision took a quantum leap when a group of researchers from the University of Toronto developed an AI model that surpassed the best image recognition algorithms, and that too by a large margin. The AI system, which became known as AlexNet named after its main creator, Alex Krizhevsky, won the 2012 ImageNet Computer Vision contest with an amazing 85% accuracy. The runner-up scored a modest 74% on the test. At the heart of AlexNet was convolutional neural networks, a special type of neural network that roughly imitates human vision. Over the years, CNNs have become a very important part of many computer vision applications and hence a part of any computer vision course online. So let's take a look at the workings of CNNs. CNNs were first developed and used around the 1980s. The most that a CNN could do at that time was recognize handwritten digits. It was mostly used in the postal sectors to read zip codes, PIN codes, etc. The important thing to remember about any deep learning model is that it requires a large amount of data to train and also requires a lot of computing resources. This was a major drawback for CNNs at that period, and hence CNNs were only limited to the postal sectors and it failed to enter the world of machine learning. In 2012, Alex Krizhevsky realized that it was time to bring back the branch of deep learning that uses multi-layered neural networks. The availability of large sets of data, to be more specific ImageNet data sets with millions of labeled images and an abundance of computing resources enabled researchers to revive CNNs. So, let's talk what exactly is a CNN? In deep learning, a convolutional neural network or CNN is a class of deep neural networks, most commonly applied to analyze visual imagery. Now when we think of a neural network we think about matrix multiplications, but that is not the case with convolution. It uses a special technique called convolution. Now in mathematics, convolution is a mathematical operation on two functions that produces a third function that expresses how the shape of one is modified by the other. But we don't really need to go behind the mathematics part to understand what a CNN is or how it works. Before we go to the working of CNNs, let's cover the basics such as what is an image and how is it represented. An RGB image is nothing but a matrix of pixel values having three planes, whereas a grayscale image is the same but it has a single plane. Take a look at this image to understand more. For simplicity, let's stick with grayscale images as we try to understand how CNNs work. The image shows what a convolution is. We take a filter/kernel 3x3 matrix and apply it to the input image to get the convolved feature. This convolved feature is passed on to the next layer. In the case of RGB color channel, take a look at this animation to understand its working. Convolutional neural networks are composed of multiple layers of artificial neurons. Artificial neurons, a rough imitation of their biological counterparts, are mathematical functions that calculate the weighted sum of multiple inputs and outputs in activation value. When you input an image in a convnet, each layer generates several activation functions that are passed on to the next layer. The first layer usually extracts basic features such as horizontal or diagonal edges. This output is passed on to the next layer, which detects more complex features such as corners or combinational edges. As we move deeper into the network, it can identify even more complex features such as objects, faces, etc. Based on the activation map of the final convolution layer, the classification layer outputs a set of confidence scores values between 0 and 1 that specify how likely the image is to belong to a class. For instance, if you have a convolution that detects cats, dogs, and horses, the output of the final layer is the possibility that the input image contains any of those animals. Similar to the convolutional layer, the pooling layer is responsible for reducing the spatial size of the convolved feature. This is to decrease the computational power required to process the data by reducing the dimensions. There are two types of pooling: average pooling and max pooling. I've only had experience with max pooling so far. I haven't faced any difficulties. So what we do in max pooling is we find the maximum value of a pixel from a portion of the image covered by the kernel. Max pooling also performs as a noise suppressant. It discards the noisy activations altogether and also performs denoising along with dimensionality reduction. On the other hand, average pooling returns the average of all the values from the portion of the image covered by the kernel. Average pooling simply performs dimensionality reduction as a noise-suppressing mechanism. Hence, we can say that max pooling performs a lot better than average pooling. CNNs have fundamentally changed our approach towards image recognition as they can detect patterns and make sense of them. They are considered the most effective architecture for image classification, retrieval and detection tasks as the accuracy of their results is very high. They have broad applications in real-world tests, where they produce high-quality results and can do a good job of localizing and identifying where in an image a person/car/bird, etc. are. This aspect has made them the go-to method for predictions involving any image as an input. A critical feature of CNNs is their ability to achieve spatial invariance, which implies that they can learn to recognize and extract image features anywhere in the image. There is no need for manual extraction as CNNs learn features by themselves from the image/data and perform extraction directly from images. This makes CNNs a potent tool within deep learning for getting accurate results. According to the paper published in Neural Computation, the purpose of the pooling layers is to reduce the spatial resolution of the feature maps and thus achieve spatial invariance to input distortions and translations. As the pooling layer brings down the number of parameters needed to process the image, processing becomes faster even as it reduces memory requirement and computational cost. While image analysis has been the most widespread use of CNNs, they can also be used for other data analysis and classification problems. Therefore, they can be applied across a diverse range of sectors to get precise results, covering critical aspects like face recognition, video classification, street/traffic sign recognition, classification of galaxy and interpretation and diagnosis/analysis of medical images, among others. Convolutional neural net is a popular deep learning technique for current visual recognition tasks. Like all deep learning techniques, CNN is very dependent on the size and quality of the training data. Given a well-prepared dataset, CNNs are capable of surpassing humans at visual recognition tasks. However, they are still not robust to visual artifacts such as glare and noise, which humans are able to cope. The theory of CNN is still being developed and researchers are working to endow it with properties such as active attention and online memory, allowing CNNs to evaluate new items that are vastly different from what they were trained on. This better emulates the mammalian visual system, thus moving towards a smarter artificial visual recognition system. That's all for today. If you have any questions, please write your question below and subscribe to our channel. Thank you. Have a good day.